Well, maybe it's a time to get started. So welcome everyone to the UTIG seminar, and it's a great pleasure and honor to welcome Chris Piecuch from the Oceanographic Institution as our speaker today. A little bit of background about Chris. So Chris is really epitomizes sort of, thinking things through carefully and doing things maybe differently and to learn something new. And it starts way, I think, after high school. Chris spent more than a year in Germany to learn German language and literature. And then after his bachelor in Rhode Island, he actually went to Malawi, where he taught, at a secondary school for a year. And then following his master's, so coming back again to Rhode Island, following his master's again, he did things a little bit differently, starting work at a private research company called Atmospheric and Environmental Research to actually find out for himself whether research is something that he would enjoy, and which fortunately for us, he did. And so on the side, he then completed a PhD in physical oceanography at the University of Rhode Island in Narragansett, which he completed in 2016. And so then transitioned to Woods Hole, where he's now currently an assistant researcher. He's really a top expert in sea level science. He's a lead PI on one of NASA's sea level change science team projects. He had been an invited speaker last year at the National Academy of Sciences workshop on solid earth science and sea level change. And yeah, so without further ado, I open the floor to Chris.
Great, thanks very much, Patrick. I appreciate the kind introduction and also the invitation to come speak. So my title today, so this is a talk I'm going to give about a paper that I published last year. And the title really says it all. I'm going to be talking about how the Florida current, which as I'll describe is an important component of the Atlantic circulation, how the flow of the Florida current has changed over the past century. And I make this conclusion actually based on observations from tide gauges, sea level observations from tide gauges. But before I get started, I want to make a few preliminary slides. First, I realize I'm giving this talk to sort of a broad geophysics audience, and also that this talk itself is pretty interdisciplinary. As you'll see as we go along, I'll hit on themes of ocean circulation, also, like Patrick hinted, sea level science, but there are also elements of what I'd call probabilistic data assimilation and uncertainty quantification. So what I'm trying to say here is that there's a lot here in this talk, and given the interdisciplinary nature of the talk and given the broad nature of the audience, there will be at least something, if not most things in this talk that may have been unfamiliar to you before today. All that to say, I'm not sure how things are usually run at UTIG seminars, but please don't hesitate to interrupt me and ask a question as we go. If anything's unclear, you don't have to wait till the end of the seminar. Please interrupt me. Also, on an introductory note, I want to define some terminology. Again, I know not everyone here is a physical oceanographer or a climate scientist, so I thought I would define my terms. I'm going to talk a lot today about ocean transport of volume, that is sort of the movement of large amounts of ocean water. And so we're talking really big numbers here. So a unit that oceanographers and climate scientists use when talking about ocean volume transport is the sphere which we sometimes denote as SV. It's defined as a million cubic meters per second. I'm defining this because I once had a geochronologist friend of mine attend one of my seminars, and he confessed to me afterwards that it took him half the seminar to realize I was talking about sphere drips and not sieverts, which is apparently another unit relevant in some geophysical fields. So SV is sphere drift, not sievert. I've given a couple of examples here of different flows expressed in units of sphere drips, just so we have sort of orders of magnitude in our mind. So Niagara Falls, this is on the order of 2 millisphere drips, whereas the outflow of the Amazon River is about 0.2 sphere drips. We can compare that to the flow of the Gulf Stream off of the US eastern seaboard as it detaches from the coast near Cape Hatteras in North Carolina, which is on the order of 50 sphere drips. So this is giving you a sense of what kind of orders of magnitude we're talking about. One last introductory slide. My title kind of gave the story away, so I thought I would just go kind of whole hog and just give you all my conclusions from the start. So if you take away nothing else from the talk, if I lose you in the details, just take away these following points. As the title says, I am concluding that the Florida current transport likely weakened steadily over the past century. This result corroborates the independent hypotheses based on other proxies and data sets that the deep return flow at depth in the Atlantic meridional overturning circulation, which I'll introduce in a moment, that's declined. Okay, so it corroborates these past hypotheses. And it also supports simulations from climate models that suggest that when you have a weakening of the Atlantic meridional overturning circulation, it tends to be coupled to a slowing down of the surface western boundary current. Okay, with that, let's get to the talk. So I just introduced this notion of the Atlantic meridional overturning circulation, or as it's sometimes called, AMOC. This is sort of a shorthand that is used to describe what is a very complex three-dimensional time-evolving circulation in the North Atlantic Ocean, which I'm showing here in this cartoon. So in the larger image, I'm showing the northern North Atlantic Ocean with a bunch of colored arrows, which are meant to indicate or identify the flow of different waters in the ocean. The red arrows are meant to signify these warm surface currents, which on the whole are bringing warm, salty waters from the equator towards the poles. And once those warm, salty waters reach high northern latitudes, they experience harsh atmospheric conditions, adverse conditions that are favorable to heat loss to the atmosphere, densification, and sinking of those waters. That's what's indicated, again, in a cartoon sense by these yellow arrows to the north. Once at depth, those waters return equatorward, as indicated by the blue arrows, kind of completing this sort of circuit, the net action of which is to transport heat northward. I'm showing the same thing on the top left, but in sort of a more precise shorthand. This is the meridional overturning circulation stream function. This is what you get if you take this complex set of flows and sum them up in a longitudinal sense across the basin. So in this inset to the top left, we have latitude running on the x-axis in the Atlantic, depth in the ocean from surface to bottom, going from top to bottom on the y-axis. And what you see, if you look at the blue shading and the the clockwise arrows, this is indicating that same circuit that I mentioned, poleward flow of warm waters near the surface, sinking and water mass transformation at high latitudes, and then return flow at depth. Now, this notion of the AMOC is relevant for a broad number of fields in Earth science. Of course, it's relevant in fields like climate variability, climate stability, and also abrupt change. For example, the AMOC has been implicated in past abrupt climate change events since the last glacial maximum. Think of things like the Younger Dryas. What the AMOC is doing is also relevant, as I'll show you, for concerns about coastal sea level rise. Due to the equations of motion, as I'll show in a few minutes, these two fields are coupled. So changes to one, to the AMOC, say, tend to be accompanied by changes in coastal sea level. And even if you're not an ocean physicist or a climate physicist, the AMOC is relevant for fields like carbon cycling, biogeochemistry, and ecosystem productivity. And in all these fields, in all these different subdisciplines of Earth science, it's relevant to know the time evolution of the AMOC. How did AMOC change in the past? How is it changing now? And how may it change in the future? And those concerns have motivated the establishment of an Atlantic-wide observing system, which I'm showing in a shorthand here. So on the left, we have, of course, a map of the Atlantic. And all of the colored lines that go across the basin with the different acronyms, these are all the nominal locations of different long-term observing systems of the North Atlantic circulation. I won't bore you with all the acronyms, but suffice it to say we have about half a dozen of these long-term monitoring arrays in place. On the right, I'm showing some of the time series from those observing systems. Maybe some of you in the audience are familiar with some of these or maybe all of these observing systems. The plot on the right is such that we have time running from past to present as left to right. The colors are corresponding between the map and the time series, and the y-axis of all the figures is showing transport, again, in those units of Sverdrup that I introduced before. So these are really valuable data, very expensive, very difficult to make, and they form our modern understanding of how the AMOC behaves. The one problem if we're coming at this from the perspective of long-term climate change, is that these records are so short. Again, so look at the y-axis of that plot on the right. It only goes back to 2000. That is, these data sets at most are covering 2 decades, which again is an incredible feat of ocean observing, but it really is just too short if we're trying to make statements about the longer-term evolution of the AMOC. So what do we do? Questions of AMOC remain relevant, but we don't have these long instrumental time series. Well, in that case, many authors have turned to proxy records. By proxy, I mean any physical variable, geological variable, chemical variable that is not itself the AMOC, but may exhibit a systematic relationship to changes in the AMOC. I'm giving 2 examples from the published literature of proxies that have been used to infer AMOC, some in the sense of climate scientific proxies, others in probably the more familiar paleoceanographic context. So on the left, I'm showing a plot from an earlier paper by Levka, Cesar, and others in 2018. These are results from climate models. So you can see all the different climate model acronyms in the color bar to the left. The scatter shows a value from each one of those climate models with the colors corresponding. And what Cesar and colleagues are showing, again, on the left, is that they're plotting 2 quantities against one another. They're looking at centennial, so century-long changes in the AMOC. That's what's plotted on the y-axis. They're plotting those against what they're calling an AMOC index change on the x-axis. What's an AMOC index change? You'll notice the units of that are degrees Kelvin per century. What they're defining as an AMOC index is actually the sea surface temperature over the subpolar gyre. So what Cesar and colleagues are showing is that there's a strong correlation, at least in these models over the time period they look at them, between changes in the AMOC and changes in sea surface temperature, such that a stronger AMOC, you're transporting presumably more warm waters, thus raising sea surface temperatures, and vice versa. Another example of a proxy is shown on the right. This is more in the traditional paleoceanographic sense. This is from a paper by McCabe and colleagues in 2017. And what they're showing is that you can infer changes in the velocity of deep flows. So deep flows in the ocean, part of the return flow of the AMOC, based on the mean grain size of sortable silt in sediment cores. The idea is that if you have a stronger flow, you are capable of transporting larger grains of sediment. Okay, so you can see that in the plot here where you have a strong correlation between mean sortable silt size, which is shown on the x-axis in units of centimeters, micrometers, and the flow speed on the y-axis in units of centimeters per second. So these are 2 examples of proxy records that are used to say something about the past evolution of the AMOC. So some authors have sort of collected these proxies from the North Atlantic and tried to make the case that these proxies are all telling the similar story that over the past couple of centuries, the AMOC has undertaken an unprecedented slowing. So this is bear with me here, it's a very busy figure, but this is a figure that was just published a couple of weeks ago by that same author, Levka Cesar, and her colleagues in a paper in Nature Geoscience. So let me orient you here. So in the top right, we have a map inset, which is showing you the region. Again, we're in the northern North Atlantic. Each of the colored diamonds, if you will, is the location of one of the proxy records they look at. And the colors of those diamonds in the map correspond to the colors of the proxy time series shown in the various time series panels below. In all these panels, we have running on the x-axis time, again, past to future is left to right. And on the y-axis of all the plots, we have various proxies, things related to ocean temperatures, different nitrogen and oxygen isotopic records, again, those sortable silts that I just mentioned, all kinds of different proxy records that the authors believe are informative of the AMOC. And we could really spend all day talking about this plot, but for purposes of this talk, what I want to emphasize, and this is what the authors of the paper are trying to emphasize, is that no matter which of these proxy records you look at, they argue, as you go from past to present, when you hit about the Industrial Revolution, you get the beginning of a strong decline of the AMOC, which is then further accentuated once you hit about 1960. So these authors are claiming, based on these proxies, that you have 2 abrupt recent changes in the AMOC, one right around the Industrial Revolution and a even more prominent one around 1960. So again, these authors and others have tried to make the case that, based on proxy records, the AMOC has recently weakened or is weakening. And that's big news. This paper actually has prompted, you may have seen, depending on what news source you read, either the BBC or the Washington Post, or this is from the New York Times, all these stories that have been published about this weakening of the Atlantic circulation and what it might mean for North Atlantic climate. So again, this is the image of this really, if you haven't read this story, please go read it. It's this really fabulous piece of science journalism, very interactive, lots of helpful graphics, and it's a very good storyline written by Moises Velasquez Manoff. And so stories like this have gotten a lot of press, but maybe they're a little bit premature. The Cesar paper perhaps didn't look at all the proxies that were out there. Here's a more thorough compilation of sortable silt records, for example, by Paula Mafa Sanchez and her colleagues. So this is a review paper published a couple of years ago. Again, we have the same format of a map inset showing where all these records are coming from, okay, with corresponding colors, and the time series of those sortable silt records. Again, the way to read these sortable silt records, we have time on the x-axis, mean grain size of the records on the y-axis. And the way you read this is that, again, larger mean grain size indicate presumably a stronger velocity, so a stronger transport, presumably. And sure, while if you look at the bottom right panel, this is the gray and the blue and the purple, these are the sortable silts considered by Cesar and colleagues. They show, once you hit about 1800, this drop in the, this decrease in the mean grain size of sortable silts, presumably indicating a weakening of the transport. But you can kind of pick whichever time series you want. Again, I know we could talk about this plot all day, but suffice it to say, this plot shows that things are a lot more complicated. These are all records that are collected along the path of the deep return flow. That's what's indicated by the thick blue arrow in the map. This is tracing out the mean pathway of the deep return flows. And so we're looking at these sortable silt records from the return flow path of the AMOC. These different records all show different stories. Okay, so it's not immediately obvious that there is this large scale weakening of the AMOC, at least as revealed by the sortable silt records. Couple results like this to papers like this one from Kyle et al., published last year in Nature Geoscience. They're not looking at the paleoproxy records. They're trying to critique some of the proxies that have been used in the past, particularly that temperature-based record I introduced before. I told you that this paper by Cesar and colleagues tried to make the case that you have a strong correlation between AMOC strength and sea surface temperature in the subpolar gyre, such that if you have warmer temperatures in the subpolar gyre, that indicates a stronger AMOC, and vice versa. Cooler temperatures in the subpolar gyre indicate weaker AMOC. That's the basis of statements like papers by Cesar and also previous papers by Stefan Ramsdorf, for example. This nice paper from Kyle et al., it's a modeling study, and what they show is that the relationship between AMOC and sea surface temperature is not unique, okay? Depending on what period the model covers, whether it's a pre-industrial model run, whether it's a model run of the present historical period, whether it's a future model run, and the nature of the forcing, you can actually get different relationships. In other words, a different amount of AMOC change per unit SST change. That's what's shown on the right here. That all this scatter is meant to show that you have all these different slopes, all these different regression coefficients between AMOC strength, which is on the y-axis, and what they're showing on the x-axis, this WHI. This is the same thing shown by Cesar. This is WHI stands for warming hole index. So the warming hole is the name that's been given to this region in the subpolar gyre. So again, the take-home point here is that if you have observations of both sea surface temperature and the AMOC in the present, and you establish a relationship to those variables, say a regression coefficient, the slope, you've got to be really, really careful taking that slope and then applying it to past records of temperature, because the relationship between those two things may not be unique and may be deceptive. So all this to say, where's the field at? Do we know if the circulation has slowed over the recent past? Well, it's not clear. Papers like Cesar et al. Sort of claim that we are currently in the midst of an unprecedented slowdown in AMOC, whereas other papers, more complete compilation of proxies, and also papers that interrogate relationships between variables in the ocean and climate models suggest, hey, hold on, there might be a more complicated story here. So what do we do? Well, models also point to a potential hypothesis that we might test. So here are some more modeling results, this time from a paper by Becky Beedling in Journal of Climate. Let's think of it this way. If we imagine that there is this weakening of the AMOC, that is to say, if those deep return flows, those return flows at depth of cold water, if that's slowing down, then by mass conservation, there must also be some other circulation changes happening in the ocean. You can't have one branch of the circulation slow down to the exclusion of everything else. This is not happening in a vacuum. Again, you have to satisfy mass conservation. So other things have to have changed, okay? So the question becomes, and what's being answered in the Beedling study is, if you have a change in the deep AMOC, what else is changing? Okay, so let's focus actually, and now I've got 3 plots here, but just for the interest of time, let's focus only on the far right plot here. So again, similar to previous plots, we're showing a scatter plot with a bunch of different colors. So the different colors all indicate results from a different model. Okay, so what Beedling and colleagues are showing here, again, we're looking at century-long trends in transport. Again, we're looking at the far right panel. On the x-axis, the numbers are indicated on the top here. We have changes in the deep overturning circulation, this delta deep. Again, this is the deep overturning circulation weakening in climate models, okay? What they're showing on the y-axis is this delta WBC quantity. This is the contemporaneous change in the surface western boundary current, so something like the Gulf Stream. And what they're showing is that these two things, the changes in the deep overturning and the changes in the western boundary current, are highly correlated. That is to say, when you have a certain change in the AMOC, the deep AMOC, that same change gets mirrored in the surface western boundary current. So that's the result that the model suggests. So this actually presents us with a hypothesis that we can test. We have the hypothesis from proxies that the AMOC is weakening. We have the simulated result from models that when you have an AMOC weakening, western boundary current also slows. So we can ask the question, has the subtropical western boundary current in the Atlantic weakened? And that's what we're going to focus on today. Okay, by the surface western boundary current, I just hinted to this, but let me make it even more clear. By the surface western boundary current, I mean the Florida current. Okay, the Florida current represents the headwaters of the Gulf Stream at its origin around Florida. So I've got 2 maps here to try to orient ourselves to the study region. So we're transitioning now from that admittedly really long introduction, but hopefully you're still tracking with me, to the result of this study. So on the left, this sort of wider view plot, we're showing the western North Atlantic Ocean, showing a bunch of color shading over the ocean. This indicates surface current speed as observed by surface drifters. The deep blues represent slower, more sluggish waters, whereas the warmer colors, the yellows, indicate faster, more rapidly moving waters. Okay. For the moment, don't worry so much about the circle and square shapes I've put along the coast. Those are the locations of tide gauges. I'll come back to those in a second. Let's look at the colors for a second. We can see the Florida current, again, the origin of the Gulf Stream, right around Cuba, Florida, and the Bahamas by this sort of snaking pattern of yellow that sort of whizzes by Miami that we can see in this boxed in region. Again, this is a region with very rapid surface speeds exceeding 1 meter per second. So what I've boxed in on the left is going to be our study region. On the right, I've zoomed into that region, okay? So we're looking at sort of southern Florida, the northwestern portion of the Bahama Islands, and a little bit of Cuba there, showing where Havana is. Now my color shading isn't surface speed, now I'm showing ocean depth. So blue is deep, yellow is shallow. What I'm trying to emphasize here is just how narrow and shallow of a region this is compared to the open ocean. I'm also showing these black and red lines that cross the Florida Straits, so between Florida and either the Bahamas or Cuba. These black lines and red lines are all the locations of historical measurements of the transport of the Florida current. Especially important for our purposes are these 2 red lines, which I've drawn a gray arrow and labeled it cables. What do I mean? These are the locations of 2 undersea telecommunications cables, which have been used since the early 1980s. So we're coming on almost 40 years now. Voltage measurements across these cables have actually been used to infer changes in the transport on a daily timescale. Let's think back. I showed that map earlier showing the current Atlantic observing system, and I said that our measurements of currents only go back about 20 years. These measurements doubled that. Okay, so these cable measurements give us measurements of the Florida current going back 40 years. That's what I'm showing here in blue. So here in blue is the time series of annually averaged transport of the Florida current from those cables. So we have time running on the x-axis since the early 1980s. The y-axis that's relevant for the transport, again, we're looking at the blue series for a moment, is on the left. These are in units of Sverdrups. A couple things to take away. One is that clearly this current, this transport varies on interannual to decadal timescale. Sometimes it's a little bit stronger, sometimes a little bit weaker. But it's not obvious, at least to me, that there is any long-term change apparent in this blue time series of Florida current transport. So we've made an improvement, right? We're trying to look further back into the past. And so this Florida current data allows us to do that, but it's only getting us back to the early 1980s. Certainly, this is not a long enough record for us to start testing those hypotheses from the proxy-based studies that the overturning is undergoing this longer-term multi-decadal to perhaps multi-centennial change. However, there is hope, by which I mean, I'm also showing this orange time series. So what's this? So the orange time series is actually the time series of the difference, the sort of spatial gradient in sea surface height. So this is measured by satellite altimeters across the Florida current. So this is the measurement of altimetry from the Bahamas minus altimetry around Florida. Again, these are measurements of sea surface height or sea level, if you will. Units are centimeters, and the scale bar here is over to the right. The point I'm trying to get across here is that these two series, the orange and the blue, are highly correlated. That is, sea level differences across Florida Straits are strongly correlated with the transport through Florida Straits. This result isn't too surprising. In fact, this correlation between transport and sea surface height difference is exactly what you'd expect from some of the most basic of large-scale ocean dynamics, namely thermal wind. So hydrostatic balance as your vertical momentum equation, and then geostrophic balance, that is a balance between your horizontal pressure gradients and Coriolis force as your horizontal momentum balances. You can manipulate those equations to derive what's on the right in this black box here, which shows that T, which is the transport of the current, is proportional to this, in parentheses, difference, zeta E minus zeta W. This is meant to indicate sea level on the eastern side, Bahamas, minus sea level on the western side, Florida, by a proportionality of GH over F. G is the gravitational acceleration, F is the Coriolis parameter, and H is essentially a scale depth. So basic ocean dynamics leads us to expect that there will be this correlation between sea level and transport. How in the world does this help us? Well, although the altimeter time series I'm showing you here only goes back to the early 1990s, this is when the modern era of satellite altimeters measuring sea level globally really started. I'm going to come back to that map I just showed earlier. Remember that map where I was showing the surface current speeds? There were all those, again, circles and squares along the coast. These are all the locations of much longer tide gauge records of coastal sea levels. Tide gauge records that were set up not so much for climate science, but for pure sort of mercantile, commercial, practical purposes. You know, when do I bring my ship into harbor, for example? Those measurements have been ongoing for decades, if not more than a century, and they provide sea level data. They provide sea level that's potentially informative for our uses. So I'll pause there to say, I'm going to try to use these basic physical principles and the much longer records we have of sea level at the coast from tide gauges to try to say something, however uncertain, about how the Florida current may have evolved in the future. So again, may have evolved in the past. So we're trying to use sea level to say something about circulation based on principles like this. But we have to be careful. So again, I'm a sea level scientist. I find it a very fascinating variable as something to sort of probe the Earth system. I always say sea level is something like sort of a whole Earth variable. Most changes that are ongoing in the Earth system, whether they're in the solid Earth, cryosphere, the ocean, the atmosphere, they all leave their imprint on sea level, okay? All of those other geophysical processes, sorry, I know I'm giving a talk at UTIG, those other geophysical signals really aren't of interest. They really are the noise to our signal, which is a circulation signal. So we need to be aware of the other processes that are ongoing in the Earth system that may contaminate our tide gauge records. I'm giving a couple examples of important processes that need to be kept in mind, processes that are geophysical in nature, that are ongoing, unrelated to ocean circulation, but that nevertheless may be imprinted on these tide gauge records. One that may be familiar to a lot of you is what's shown on the left. This is a map, a model solution of present-day rates of sea level change due only to the glacial isostatic adjustment process. So glacial isostatic adjustment, or GIA, refers to the ongoing viscoelastic response of the Earth, the solid Earth, to the last deglaciation. Okay, so yellows indicate regions with enhanced positive sea level rise. Blue indicate regions with actually sea level fall. You'll notice this pattern is such that you have these deep blues over former glaciated centers. These are regions that were formerly depressed and subsided due to the load of the ice sheets. Of course, those ice sheets have since long gone, so those regions are uplifting, and that uplift translates to a sea level fall. Compare that to the deep band of yellow that sort of rings around those former glaciated centers. Those are regions of enhanced sea level rise. These all lie along the peripheral forebulge of the former ice sheets, regions that were formerly uplifted due to the movement of mantle material laterally outward from the glaciated centers, which are now subsiding as that mantle material moves back to places like Hudson Bay. Another example is on the right. This is the sea level change pattern that would result from melting of the Greenland ice sheet. I'm showing these in units of percentage of the global mean change, the global mean sea level change. So when you melt ice from Greenland, you actually get a very strong fall in sea level in the near field. Even though you're melting ice, adding water mass to the ocean, so global mean sea level is rising, you get a regional sea level fall in the near field due to the reduction of the gravitational fields of that ice sheet. As you move progressively farther away to the far fields, you get higher and higher rates of sea level change, such that, for example, when you get to the South Pacific or the South Atlantic, you have greater than average rates of sea level change. Okay, let's not get too lost in the weeds. I'm just giving two examples here of processes that cause sea level change that may be impacting our tide gauge records that we want to be mindful of if we're going to use the tide gauges to say something about circulation. So there are physical process challenges at play. Also data challenges. So here again on the right is that same map. We're again showing our study region. Along the coast, these circles and squares are the locations of long tide gauge records. These data are really messy. So anyone who's worked with tide gauge data knows that they can be irregularly, sort of heterogeneously distributed in space and in time. I'm showing some example series on the left. So we have relative sea level, so that is the height of the sea surface relative to land. Relative sea level on the y-axis in units of meters. Don't worry so much about the absolute values. They're offset by an arbitrary amount. Only changes are relevant here. And then time since the early 1900s running along the x-axis. So you can see that there are some long series. So if we look at the light blue time series, or the green, or the purple, these are at places like in Key West, Florida, Fernandina Beach in northeastern Florida, and also Cristobal in Central America. These records go back to the early 1900s. However, other records are more gappy or short. If we look, for example, at the bottom right of this left panel, I show these really thick lines, yellow and orange and blue. These are really short, gappy time series. Unfortunately, these short, gappy time series are ones from West Palm Beach and from Settlement Point on Grand Bahama Island. That's unfortunate because these are the endpoints, the geographic endpoints of that cable. This is exactly where we want sea level data. Remember, the principle we're working on here is geostrophy, or thermal wind balance more formally. That is, we want sea level on opposite sides of the current we're trying to measure. So the fact that the records are so short in West Palm Beach and Settlement Point is a challenge, but all is not lost. If we look a little more closely at these time series, we can certainly see the signature of sea level rise. All these records are sort of increasing as we go from past to present, but they show interannual to decadal fluctuations. And those fluctuations aren't random. Okay? They're not random in time. That is, that there's autocorrelation. Each year has memory of the last year. But they're also correlated in space. For example, if we look at the light blue series, this is from Fernandina Beach in northeastern Florida, and the green series, which is from Key West in far southwestern Florida, they fluctuate in pretty close unison. What this is telling us is that sea level is a field that is spatially coherent over large scales, okay? So we're going to try to use this to our advantage. We're going to try to exploit the fact that sea level as a quantity of interest, as a variable in the ocean, is one that exhibits spatial and temporal correlation. So we're going to try to use that to our advantage. So that all leads me up to the goals of this study. So what do we have for data? Okay, so let's review. So we have almost 1,400 gauge years of annual sea level from these 46 tide gauges I've shown in these couple plots. Okay, the longest data go back to 1909. This is places like Cristobal in Central America. These are coming from the Permanent Service for Mean Sea Level. Okay, so we have the sea level data. We also have almost 40 years of annual Florida current transport measurements from those submarine cables from NOAA. So these are the two data sets we're working with. And I have a couple of goals here, and I've hinted to them in the slides coming up to now. As I just said, I'm going to try to exploit the fact that sea level is a field that exhibits spatial and temporal covariance, and to use that structure to try to fill in all the gaps of those gappy tide gauge records, so that instead of 46 tide gauge sites, some with long records, some with short records, some with complete records, some with gappy records, they are complete records at every location for the past 110 years. Okay, that's goal number one. Goal two is to then, or not in a sequential sense, but simultaneously use those sea level measurements in tandem with the available transport measurements since the early 1980s to essentially constrain a relationship between the two that allows me to extrapolate back in time to estimate with uncertainties what the Florida current transport has done since the early 1900s. So this is kind of a multifaceted, challenging scientific question. We've got a challenge that is sort of riddled with these uncertainties, right? You know, we have the uncertainties related to what processes are contributing to sea level change. How does sea level itself relate to circulation? These are all physics type questions with uncertainty, but they're also data questions. How do I deal with these gappy short data sets? Well, to tackle a problem like this, the approach I'll use, and I'm not going to go too much into detail. I just want to give you the sort of philosophical essence of what I'm doing here. I'm using Bayesian data analysis. Okay, so the problem is stated as follows. I've got a bunch of very imperfect data, which I'll collectively call Z. And I'm interested in making some posterior statement about some oceanographic process I'll call Y. And the physical process itself, how it evolves in space and time, and the relationship between that variable and the data. Let me say that the rules that govern those relationships and evolutions are governed by some parameters, you know, things like spatial covariance scales or error variances, things like that, which I'm going to collectively call theta. Now, I know Z, that's the data I have. What I don't know is Y, how sea level evolved, how the transport evolved. I also don't know those parameters. I don't know what the dominant spatial scales are. I can look at a plot like I just showed and make the inference that, hey, these spatial scales are large, but as to a number, I don't know that. So they're uncertain. So what I'm trying to do is what's shown in the bottom left. This is just a version of Bayes' rule. So again, this is kind of statistics 101. Very simple idea here, but extremely powerful for our purposes. So my end goal is to make this posterior inference. What is the probability of Y and theta? What are the probability of my process and my parameters given the data I have? And Bayes' rule gives me a mathematically coherent way to break that down in, as shown on the right here, in terms of questions of physics, what I'm calling a process level, you know, writing down an equation for how I believe these processes evolve in space and time. Separate from data level considerations, how did the imperfect data relate to the process? And then finally, a prior or parameter level, you know, how can I codify my prior knowledge of these parameters? So Bayes' rule gives us a way to formalize what would otherwise be sort of this intractable, there's just too many uncertainties in this problem. It allows me to sort of break it down in this coherent way, specify individual equations, which again, I'm sort of keeping you in the dark because I think it'd be too much in the weeds, but I'm very happy to talk to interested folks offline about this of the nuts and bolts. But suffice it to say, I'm able to break the problem down into mathematically tractable sort of chunks and make an inference. So what I do is just that. I specify these models, these process level models. I write down equations for how sea level evolves in space and time, how it relates to circulation. I also specify these data level equations or measurement models, might be a more familiar term. where I say how the cable measurements relate to transport, how the tide gauge records relate to sea level. And then finally, I write down, I place prior distributions on all my parameters, okay? This sort of problem can't be evaluated analytically, so I evaluate the model numerically using Markov chain Monte Carlo, so a Gibbs sampler. So for those who know this sort of stuff, certainly nothing new. I mean, this goes back to the statistical literature of the 1990s, so certainly not paving new ground here. The last bullet point is important. So what results here is I get a fully probabilistic posterior ensemble of solutions. So what I get out of this model, remember, I'm asking, how did circulation change? This model doesn't just give me, means and variances, summary statistics. It actually produces this ensemble of thousands of potential transport histories, thousands of potential scenarios for the Florida current transport, all of which are equally likely, uniformly likely, given the available data, and all internally consistent with the model physics. Okay, and that's important because it allows me to sort of ask the kind of questions that I'm asking, which really relate to subtle spatiotemporal statistics. So after all that, here's the result. So this is my probabilistic estimate. After I assimilate the tide gauges and simultaneously assimilate the cable data, this is what I get for my estimate of Florida current transport. So a lot of things here, so let me walk you through. Orange is the observed transport. This is from those cable measurements that I showed before. So that's just repeating what you've already seen. All the different blue colors relate to things that are output from my Bayesian model. So again, to orient you, we've got x-axis is time, y-axis is transport and spare drips. The thick blue line is the posterior median estimate, so the best estimate of transport. The light blue shading is what I'm calling the pointwise 95% credible interval. So this is very similar to maybe the plus or minus 2 sigma that most people are familiar with, but again, in a Bayesian sense. One thing that's important about this value is that it's a local measure of uncertainty. That is to say, the way you interpret this shading is that, pick any year you're interested in. The way to read this is that there's a 95% chance that the true value falls within that range. Again, in that particular year. That's a local measure. You can imagine more global measures of uncertainty, and that's what I'm showing by these sort of the wider dash lines. What these are indicating, this is the 95% pathwise credible interval. This is a global measure. The way to interpret it is there is a 95% chance that the entire century-long evolution of the transport never strayed outside those bounds. So, the more global measure of uncertainty. And then finally, just to emphasize again this probabilistic ensemble nature of the solution, I'm showing as the two thin blue lines, just two totally randomly chosen ensemble members to show you what the individual solutions look like. Again, each of which is uniformly likely given the data and the model. A few things just to point out as we go. So if we consider the uncertainties, how big the error bars are. If we look after 1982, so more to the right in the plot, they're pretty small. This makes total sense because this is when we actually have the observations from the undersea cables. The estimate's tightly constrained as you would hope, so the error bars are very narrow. As soon as you go back in time, back before 1982, the error bars grow, and actually they grow quasi-linearly into the past, okay, because we no longer have the transport data, and our inference is largely constrained by the tide gauge data, which have a more uncertain relationship to transport, and they become gappier going back in time. Okay. If we look at the time series, we can see that there is interannual to decadal variability, which I could talk a lot about, but I'll hold off here. What I want to emphasize is that, and I'll show this more clearly in a moment, there is, I believe, a subtle decline in this transport. That is, it seems to be that there is potentially a long-term decline in the transport. Let's look at that more clearly. Here are a couple of histograms. Again, remember, this is a probabilistic ensemble, so I can compute these probabilities in this sort of histogrammatic sense. Let's consider the average transport over different periods. On the left is the mean transport histogram. So on the y-axis is the fraction of ensemble members. On the x-axis is the transport. I'm computing the mean transport over 3 different periods. The blue is the full study period, 1909 to 2018. Again, that period is constrained by how far back the tide gauge data go. I compute a mean over that time period of 32.6 plus or minus 1.4 spare drips, where the plus or minus is the 95% posterior credible interval. Okay. Compare that value to the mean over 1982 to the present. This is the yellow bar. It's much tighter. It's much more strongly constrained, again, because we have the data over that period. Okay, so that's very well constrained at 31.8 plus or minus 0.1 Sverdrup. But compare that to the value over 1909 to 1981. This is the period where we don't have measurements. Okay, a much wider histogram, again, reflecting the uncertainty due to the fact that we don't have direct transport measurements during that time. There's about an 86% chance that the transport during that earlier period, 1909 to 1981, before we have measurements of transport, that's stronger than the transport during the latter period since 1982, when we do have data. In other words, this is the first sign that we're getting that the transport may have declined. In other words, what we're measuring as a transport is already in some weakened state. Let's take another look at this. On the right is maybe a more quick and easy way to get to the change. This is just the long-term trend. So what I've done is for each of these thousands of ensemble members, I've computed the linear trend over the 1909 to 2018 study period, and this is the histogram. So in the usual mean plus or minus 2 sigma sense, the transport change over the past 110 years is minus 1.7 plus or minus 3.7 Sverdrup per century. Depending on the question you're asking, the result is significant or not. Certainly this is, we cannot distinguish the trend from zero at 95% confidence, say. But my question is a little bit simpler. I'm asking, can we identify the sign of the change? Is the current weakening? And based on this histogram, I compute that there's an 82% chance, so likely in sort of the old IPCC parlance, it's likely that the transport declined. Okay, so basically 6-to-1 odds that it declined over that period. So you might ask, well, how sensitive is that inference of a decline to that 1909 to 2018 period? There's nothing special about 1909 to 2018. I selected that because it's the longest period accessible to me, given my data. But the answer is that conclusion sensitive is no. What I'm showing here is a matrix where I consider the change in transport between all possible pairs of decades. So I have on the y-axis my start decade, anywhere from the beginning of the study period in the early 1900s to the present. And then I have the end of that change period on the x-axis. Okay, and the way to read this is that the colors indicate the change from start to end. Blues indicate a decline, yellows and greens indicate a strengthening, and the grays indicate regions where the change is not significant. I guess the quickest way to say this is that there's a lot of blue here, indicating that for a lot of these periods, you get a significant decline, especially as you start moving away from sort of the diagonal of this matrix. That is to say, as you have periods that are separated by longer times, that is, you're not considering sort of a change over a decade, but change over several decades. As you move further and further to the bottom right corner of this matrix, again, you're considering longer periods, you get almost always this deep blue color, saying that basically for any period you pick, provided it's longer than, say 40 or 50 years, you get this decline. So my argument here is that no, my conclusion of a decline is not sensitive to the time period. In fact, this result here indicates that the decline has been fairly steady over the past century. One last way to look at this is that, if there wasn't a decline, if it was just sort of the stationary process, okay, it would be uniformly likely that any extreme, whether a minimum or a maximum, happened at any point over the period. Okay. However, if there was a long-term weakening, it's much more likely that the maximum transport happened toward the beginning when it hadn't weakened, and that any minimum happened later in time. Okay, and that's what I'm showing. We'll focus on the top plot here. What I'm showing here is the probability that the maximum decadal or minimum decadal transport happened at any time. What I want to draw your attention to, again, looking at the top plot, this top histogram, again, fraction of ensemble members on the y, time on the x, is this sort of clustering, this little hill of blue around 2010. What this is telling us is that there's about a 75% chance that the weakest transport has occurred over the past couple decades. Okay, whereas if we look at the orange, this is when the maximum happened. It's likely that maximum happened before the mid-1930s. Okay, and the bottom plot is kind of showing the same thing. After the long-term trend has been removed, you change some of these probabilities, and long story short, it's saying that the probabilities in the top histogram can't be explained by decadal variability. It's very much a function of the long-term trend. So those are different ways to look at this question of has it declined. And I think that this is pretty convincing evidence that, given the data we have, signs seem to point that way. I know I'm running short on time, but let's see how much we can get through of this here. So what does this mean? This is the interpretation section. What does the Florida current transport mean? And what does it allow us to say about other changes that might have happened? Well, remember the earlier Cesar and Ramsdorff studies that suggested that the broader overturning circulation was weakening. That inference is partly based on the fact that over the past 110 years, sea surface temperatures have cooled over the northern North Atlantic, this so-called warming hole that you might have heard of. That's what I'm showing here on this plot. These are trends in sea surface temperature over the last 110 years. Blues are cooling, yellows are warming relative to the global average. I want to draw your attention to this sort of region in the subpolar North Atlantic where you have this deep blue cooling. Here's the time series over that region showing that there has been a fairly steady cooling over that region. Again, this has been the basis of that statement that the AMOC is declining. Let's think about this for a second. If you fit a trend to this line, you get about minus 0.6 degrees Celsius per century. Now, all else being equal, that declining sea surface temperature implies a heat flux at the sea surface such that the ocean is taking up heat from the atmosphere. If you work out the math, it works out to something like about 16 watts per meter squared per century. Now, if the ocean is taking up that much heat and it's just storing it locally, say between 27 north, which is where the Florida current is, and say Bering Strait on the other side of the Arctic, if it's storing all that locally, it would imply a change in temperature over this whole basin, top to bottom, of about almost half a degree Celsius, which is much larger than what's being observed. So that means that all this heat being taken up can't be stored locally. That heat flux has to be balanced by changes in ocean heat transport, okay? So what we're finding is that we're revealing two physical constraints that need to be satisfied. Remember in the beginning I said, any change in the deep overturning has to be balanced in the sense of mass conservation by a change in some other current. So the question is, does the Florida current provide that? Now we have another constraint, which is heat balance. We know that any changes in transport across 27 north have to be such that the heat transport divergence they cause balances this apparent heat flux. So let's in my last couple of slides, let's make this a little bit more formal. We're trying to satisfy two constraints. One is mass conservation. I'm saying there can be no net mass transport across 27 north in the ocean. That's what's written by this equation with the different psi's. So psi is the oceanographic transport. I'm using the prime notation to mean a centennial trend, and the subscripts of F, D, and T are indicating different circulation. So psi sub F is the transport of the Florida current. Psi sub D is the transport of that deep return flow. And then finally, just to be complete, the psi T is everything else. It's the sort of the upper ocean, interior ocean gyre, the sphere drip gyre, if you will. I'm saying if you sum up all those trends, it's got to be zero. Okay, this is mass conservation. And second equation is that heat conservation constraint I just said. So the psi's with the primes and subscript are all the same: Florida current, deep overturning, and interior thermocline transport trends. And the thetas are representative ocean temperatures over those same sections: Florida current, deep overturning, and interior thermocline. So this is, the left side is the heat transport divergence in the ocean. I'm saying that must balance what's on the right hand side, which is the heat flux, where Q is the heat flux trend. The subscript AS means air C, and then A is the area over which that flux happens, and CP and rho are heat capacity and density. And I'm noting that the heat flux Q sub AS is a function of sea surface temperature. You have the short wave, long wave, evaporative and latent and sensible heat fluxes that are, some of them are functions of SST. If you manipulate those equations, solve for what we don't know in terms of what we do know, you can come up with these equations that I'm boxing in on the top for the change in the deep overturning, psi prime sub D, in change in the thermocline recirculation, psi prime T. Okay, and these are all functions of sea surface temperature, the change in Florida current transport, and those background mean ocean temperatures. Okay, so this is just a rearrangement of the principles of mass conservation and heat conservation. We can use these. We know the SST change. I just showed you that. I have made an inference on the Florida current change, so we can make an estimate of the change in the deep overturning, which is what we're trying, that hypothesis we're trying to come around to corroborating. So here, this is essentially the last result here. On the top, I'm showing my inference in trends in the deep overturning. So these are cumulative trends. The way to read this is, at any given time, so say 1910, the value that's shaded thick is the mean, dark shading is plus minus 1 sigma, light shading is plus minus 2 sigma. The value of 1910 is the trend from 1910 to the present. The value of 1920 is 1920 to the present. So all the years represent the start period of the trend, and they all go to the present. The bottom is the same thing, but for that thermocline gyre. Okay, let's start with the top plot. What we see is that if you go from about 1910 to, let's say, maybe about 1950, the trend in the deep overturning is distinguishable from zero at least 1 sigma, okay? And the sign convention here is such that a positive value is a northward transport. Northward is in the opposite sense of the mean flow. So the return flow is southward. So a northward trend is a weakening of the mean transport. So this result suggests that for periods from about 1910, 1950 to the present, you do have this probably significant weakening. If we go more to the present, shorter, more recent trends, you start getting more overlap with the error bars with zero. They become not distinguishable, not significant. So our results do support a weakening of the overturning over sort of 70 to 110-year timescales. Very different story if we look at the thermocline. Again, I've made sure that the y-axes, which show transport per century, the trend, they're the same between the two. You've got these massive uncertainties. So both these inferences, the deep overturning in panel A and the thermocline recirculation in B, they're both based on the same principles and the same input data, the SST and the Florida current. Why are the thermocline recirculation estimates so much more uncertain? Well, this is a function of ocean temperature gradients. Mainly, it's a reflection of the fact that the ocean is much more strongly stratified vertically than it is horizontally. So this is a section, this is basically my last slide here. This is showing mean temperature in the ocean along 27 North. So we've got Florida and the Bahamas to the left. We can all see the mid-Atlantic ridge, and then Western Africa to the right. What we see is that we have very warm waters on the surface and very cold waters at depth. So if you have a change in the overturning that's acting on the deep waters, you have this very large temperature gradient. Okay, that in other words, your heat transport due to the combined action of Florida current and the deep overturning is very sensitive to this temperature change. In other words, a very small change in those transports affects a big heat transport. Okay, so there's only a little bit of wiggle room for the deep overturning to move around in, if you will, to satisfy both those mass and heat conservation constraints. Contrast that with the thermocline. So again, the Florida current is acting on temperatures in this little wedge to the top left, these warm waters. The thermocline transport is acting on these broader waters in the open ocean. They're very similar temperatures. So a change in these transport actually affects a much smaller heat transport. So there's a lot more room that this transport history can move around in, while at the same time still satisfying mass conservation and heat conservation within uncertainty. So again, this difference is due to the nature of ocean temperature stratification. So I'll end with my same points from the beginning. If you lost me along the lines, somewhere along the lines, here my conclusion: the Florida current transport likely weakened over the past. This corroborates past hypotheses that the deep overturning also over that same time, and it supports relationships from climate models that these two currents, these two circulations are coupled on these timescales. I know I went pretty quickly through that. If you're interested, all this is published in the paper that came out late last year in Nature Communication, so it's open access. Feel free to go read it. I'm happy to talk with you afterwards if you want to get in touch. And I know I've gone a little bit long on time, but I'm happy to take any questions if there are any. Thank you very much.
Yeah, wonderful. Thanks for a great talk, Chris. And we do have questions. From the first one I see is Charles.
Yeah, it was a really fun talk. I liked how you kind of were very free with pulling together different concepts, and it helped you all out in the end. So the question I have is that I would expect the overturning circulation to slow down because of the surface waters warming up. I guess that's the typical explanation in the CMIP type of models where, but you're really working on the principle that, so let's say I would expect because of warming in the north, the overturning circulation would slow down. But in your model, the slowing down should make it cooler, right? Rather than warmer. So those things kind of act against each other. And I would think also that the way you get around those two things is that you're paying close attention to the heat loss from the ocean, the Q. But I would think those observations are pretty poor.
That's a great question. Yep.
So my question is, like, these two different types of way of thinking about the system act in opposite ways, and the policeman is poor observations. So
yeah, no, I mean, great. I mean, there's lots of facets to your question. I'll try to comment on, at least touch on all of them. Yeah, you're right. I mean, so one, sort of a confession. I mean, this paper is very kinematical in the sense that I'm really not asking those driving questions. So those sort of aren't accessible to me, but those points are really valid. So I'll grant those, and I'll say that based on these results, I haven't sorted out those questions of sort of those drivers. Your point about the uncertainty in the SST measurements, yeah, great one. So I focused a lot of my effort on uncertainty quantification. I'm sorry, I'm really embarrassed, but I realize I've locked my cat in this room with me, so I'm going to let him out, and I'll be right back.
Okay. Good.
I was going to say that usually Chris's talks were cat influence, but then this picture is dog influence.
Oh, so. No, well, thankfully we've got the dog. So my wife just got home, so she's got the dog under wraps, but I was blind to the cat, who was the sleeper agent. Sorry. So yeah, I'm back to your question, Charles. So in this paper, I sort of went to pains to really rigorously do the uncertainty quantification with respect to the tide gauge measurements and the Florida current transport. So the result that should be interpreted as a rigorous uncertainty quantification really is that time series that I showed of the Florida current transport. But you're exactly right. Once we start looking at those SST data, so again, for that analysis, that was kind of part of the discussion section. There, I was just drawing from sort of a gridded estimate, which again, that's based on sparse, gappy, say bucket measurements and other things in the subpolar gyre that perhaps warrants a thorough, uncertainty quantification as well. So I didn't go there. But I'll grant your point that the results are probably, in that respect, in those later slides I showed, probably more uncertain than my results led on. But again, those are more sort of interpretation. What is the meaning of this result that I found? But I mean, that's sort of a great direction for a next study. How do these things change if you more rigorously account for uncertainty there and start asking these questions about sort of drivers, like you said. So try to touch on everything. Thanks.
Great. Thank you. Are there any further questions? Or maybe to people thinking again, and maybe, well, there's Sean. Sean has a question. Sean Gulick.
Yeah, that was a really fantastic talk.
Thank you.
And super clear. I guess my question is what's next question? I mean, where's the big, I mean, some of these data sets take decades or you'd really like millennia, right? How can we make the next significant leap given that challenge of the observational timescales?
Yeah, well, I mean, it's right. I mean, so I could interpret that question lots of ways. I'll interpret it the broader way. So I could take that as what's next for me. What am I interested in the next question? But I think you're probably pointing to next for the community, and that's probably more useful to people than hearing what I want to do. No, it's a great question. So yeah, I mean, this is not a problem that's going away. I mean, there's a whole there was a nice paper last year by Daphne LaBelle is the lead author in GRL. And what she's done is saying, okay, we've got short records. How long do the records need to be so that we can start, given the noise in things like the rapid measurements of 26 North, given the noise that those observations show, how long is it going to take to detect the kind of signal we see in seedment models? And her results are, well, between 30 and 70 years. So again, this is not a problem that's going away. So what do we do? Well, one thing that I get really excited about, because I'm trained as a physical oceanographer, I am by no means a paleoceanographer. But what's great is that, at the same time that these questions become more apparent and glaringly obvious to us, you have a real proliferation over the past decade or two in these relatively high resolution proxy records that come into the modern. That's great because, you allow for this overlap between the paleo records and the modern instrumental records at really a key time, right? Because it's sort of this confounding problem. Most of our longest instrumental records, think of sort of SST or surface temperature, tide gauges, those are coming right online as the climate system's emerging from the little ice age. So you have this sort of very confounding data issue of how many degrees of freedom do we really have to separate out these different processes? So the fact that you have the overlap between these high resolution modern proxy records in the instrumental records, great. But what it means is that, and I'm excited by this, is that it means that physical oceanographers, climate scientists, and paleoceanographers, and maybe sea level scientists, sort of need to start coming up with these new collaborations. So that's, I mean, my very subjective personal opinion of where the next real sort of progress is made is saying, you know, observations are great, we need them, let's keep them going, but we can't pretend that we're going to, you know, find the smoking gun of that weakening AMOC in something like the rapid record anytime soon. We've got to really sort of synthesize all those records and challenge our understanding of what those proxies mean. So that's for me the next step, is that collaboration.
Yeah, that's great. Thanks.
Okay. Any further question? Maybe I have one to you alluded to the thermocline, or basically the Swerdrup recirculation.
Yeah.
And you kind of implied that it's probably not plays a major role, but the idea of basically just the compensation between just the weaker recirculation, that basically a wind-driven circulation that would be more or somewhat important, and not just the thermal wind balance or the geostrophic circulation, so to speak. You want to sort of make a statement about this part?
Yeah, no, thanks for asking. I mean, at that point in the talk, I admit I was kind of rushing to finish, so maybe, you know, I lost folks there, but no, it's a great question. So what did I find? So I showed that one result, but I really tried to pick apart the various elements of what can I say with respect to the gyre. So again, I focused a lot of my talk, you know, what's going on in Florida Straits, that really narrow channel, what's going on in the deep ocean, but this question of what happened in the open ocean, sort of in the upper layers, is important. And so in the paper, I go through a couple different exercises. The result I showed here was actually really, really consistent with what I found by looking at. So there are gridded, what are called atmospheric reanalysis data sets, which provide gridded estimates of things like winds over the past century or so. So if you look at those, you can compute through simple ocean physics, you know, what would be the change in transport of the wind-driven Sverdrup gyre, for example. And kind of hilariously, you get equally big error bars. You know, you pick reanalysis data set A and they say, oh, it's weakened, and you pick reanalysis data set B and they say, oh no, it's strengthened. There's not even agreement to sign if you compare different reanalysis data sets. That's one thing. You can also sort of say, okay, well, we have these rapid data for the past, you know, decade and a half. We can't get long-term trends, but we can get basic time series properties, things like, you know, dominant length scales of variability and variances. And you can sort of run these simple toy simulation experiments. Say, okay, if I've got a time series that's a pure stationary noise time series, but it has these time scales of variation and these amplitudes, let me just estimate those values, simulate it for a couple hundred years, and just say, what's the realm of possibilities of a stochastic trend? Again, you're simulating a pure stationary process, but you're saying what can sort of it randomly do over the course of a century? And you find, again, similarly with things like the Antilles current, which is a subsurface western boundary current, sort of still over the open ocean, you can easily get things like plus or minus a Sverdrup per century, which is again on the same order of what I infer for the Florida current. So bottom line, what do I say about the wind-driven interior gyre? It could have really done anything. It could have strengthened, weakened within some really big envelope. But the important point, while I say I can't really say anything there, given how strong the constraints of heat conservation are, that nevertheless, even though you have that big uncertainty, it nevertheless allows me to say something more definitive about the deep overturning because of the issue of ocean stratification being so much stronger in the vertical than the horizontal. So that's as far as I can take it. But, you know, going back to the question that was just asked by Sean, you know, getting at how did the gyre change? Can we say anything about that? That's sort of one thing that I'm actually interested in, sort of working with a student right now to sort of see if there's anything that the tide gauges can help us with on that front.
Great, thank you so much. I see there are no further questions, and we're already over time. So let's thank Chris again for a fantastic talk.
Thank you all,
much, Chris. And we will now switch over to Chris, the other Zoom link for the individual meeting. So
perfect.
Thanks everyone, and bye-bye.
Yeah, thanks very much. I appreciate everyone's time.
Thanks.